Hello everyone. Welcome back to our series on thermodynamics part 2. Today we will dive into more detailed topics which will make your fundamentals clear. Understanding the fundamentals of thermodynamics is crucial for building a strong foundation in this field, enabling a deeper comprehension of both theoretical and practical applications. These basic principles will help you grasp how energy transforms and flows in various systems, from engines and refrigerators to natural processes like weather patterns. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to part 2 of Thermodynamics, a beginner's guide. Those who have missed this first episode, here is a quick recap, although I have put it up in the I button which you can go ahead and check. So in the first episode, what we started was that we dealt with what is a thermodynamics, the Greek word, and then a basic understanding. We also understood overall the first and the second law of thermodynamics, and we went into deep understanding what are the applications of thermodynamics, how it actually improves our standard of living and whatever is around us. We also looked more specifically into the history of evolution of what is called an atmospheric engine, who are the people who first discovered atmospheric engine and how it actually evolved into better engines and machines. We also looked into what are called dimensions and units, and we understood what is control volume. Now, apart from that, what we also looked is that in the last episode, I actually gave a point where you can actually spot the error in terms of what we call dimensional homogeneity. Now, I'm very thankful that one of my subscribers actually tried to explain this, and there was a little bit confusion which actually put it in the comment box. So just to clear up the basic things, here is what I'm trying to tell, that during an analysis, a relation with inconsistent units is obtained and a correction is found and the probable cause of the error is determined. Now, as you can see in this equation in the last video, the two terms on the right hand side actually do not have the same units, and therefore they cannot be added to obtain the total energy. So the solution is that to multiply the other term with the kilogram and then cancel it out, and therefore find kg and kilojoules in either side and add it. So thank you for Red, who actually put it up in a comment box, and this is what actually I tried to mend, but maybe my communication was not clear, but apologies, but this is how we actually do. So we come to what we call is the dimensionally homogeneous. I mean to say that you cancel out and then get the same unit and do the mathematical calculations. So in this video, we will first start what is called the properties of a system. So in general, what we have understood what is meant by a system, and there are certain properties which are actually in a system. So what does a property do? It defines the state of the system, which can be used to differentiate, that is to tell that this system is a little bit different from other. So the terms are basically pressure, denoted by capital T, which is the force exerted by the system per unit area. Then we have got temperature, which is denoted by capital T, a measure of the thermal energy within the system. We also denote volume by capital V, which is the amount of space occupied by the system, and we also denote what is small m, that is the amount of matter within the system. It is basically an extensive property. What we will mean by extensive and intensive property, that we will come later. So these are the properties by which we define a kind of a thermodynamical system. Now there are many other properties which goes beyond this, which are called extended properties. Among them, the first is viscosity, which is a measure of fluid's resistance to deformation or flow. It is an important flow in concept in fluid dynamics, and affects how fluids flow under various conditions. There is another concept which is called modulus of elasticity, and this is also known as Young's modulus. It measures the the stiffness of a material. It is a key property in material science and engineering. We also have something called thermal conductivity, which is the ability of a material to conduct heat. It plays a crucial role in the heat transfer process. And thermal expansion coefficient, which is the rate at which material expands with an increase in temperature. This property is important in designing systems that undergo temperature changes. Now, apart from that, there are various other extended properties which I have not mentioned, but overall, this can be told as the most important extended properties. Now from here, when we go into this kind of a property, we find that there are two types of properties which can be classified. One is an intensive property, which is independent of the mass of a system. So intensive properties are those that are independent mass of a system, such as temperature, pressure, and it can be density, etc., volume, etc. And there can be extensive properties, are those which value depend on size or extent of the system. For example, total mass, total volume, I would say, and yes, apart we can say the total mass, total volume, total momentum. These are some of the examples of what we call extensive properties. Now the question is that how do we find out the property which is intensive and extensive, and there is definitely a way out of that, and we will look into that. How do we determine all those? So we will take this kind of a system and this kind of a system where you see the mass is denoted by small v, t, p and rho, and these are the extensive properties, intensive properties. What do we mean by this kind of a figure? I will just show you into the next part of the video. So an easy way to determine whether the property is intensive or extensive is basically to divide the system into two equal parts, as you can see, with an imaginary partition as shown in this, the extensive and the intensive properties, and each part will have the same value of intensive properties as the original system, but half the value of the extensive properties. Right? May I repeat? Each part will have the same value of intensive properties as the original system, but have the value of the extensive properties. So generally, uppercase letters are used to denote extensive properties, with mass small m being an exception, and lowercase letters are used for intensive property, with pressure and temperature, that is P and T, being the obvious exceptions. Now there are some features which is very important for extensive properties. You can just go through these are very important. Depend on the amount of the matter present. If you have twice the amount of the substance, the extensive property will be twice as much. Example, volume, length, mass, energy sometimes, and the notational convention is generally represented by capital uppercase letters, but as I told, that the pressure and temperature being the I would say the exceptions. Now what is intensive properties? Here are some of the features. Independent of the amount of present, do not change obviously. Examples are temperature, density, color, boiling point, and they're represented by T, D, rho and BP, that is the boiling point and the melting point. So for example, we take mass m, though extensive, right, it is often denoted by lowercase, and P and T, though intensive properties, are commonly denoted by uppercase letters. Now in order to just give an analogy that how easy in order to understand, let us imagine this beautiful birthday cake. Although my birthday is already gone. So this cake's total weight is the extensive property. So it is actually telling that how much cake you have. Now if I take a bite of this delicious cake, then the bite of that cake will taste the same intensive property as the whole cake, regardless what is the amount that you have eaten. So the cake's total weight is the extensive property, and when I bite that, or when you bite that cake, will have the same taste as the whole cake, regardless of the amount that you eat. So this is a kind of an analogy, quick and simple layman's example of understanding extensive and intensive property. Now, in order to calculate all those things in thermodynamics going up to the atomic or molecular level, we need sometimes the equations becomes too difficult. And for that, we need a system, or I would say a mathematical model, which is called a continuum theory. Now, what do I mean by continuum theory, etc.? Let me explain you easily into the next part of the video. What is continuum, or what is continuum theory? Now, if I take this kind of a thing, just a kind of a matter, any lump, clay, brick, etc., we say that matter is made up of atoms that are widely spaced in the gas phase. Now, it is very convenient to disregard the atomic nature of substance and view it as something very continuous, homogeneous matter which has got no holes. So that is the question. Can you disregard the atomic structure of substance and view it as continuous, homogeneous matter with no holes, something like this? Absolutely, smooth, something which has got no holes. Now, this is actually what we say. So you see on the left hand side, these are gases, these are atoms of the gases, consist of tiny atoms with vast spaces between them. So the continuum idealization allows us what? To treat properties as point functions and to assume the properties vary continually in space with no jump discontinuities. So it actually, again I repeat, to assume the properties vary continually in space with no jump discontinuities. So this idealization, remember, is valid as long as the size of the system we deal with is large relative to the space between the molecules. So here you can see this kind of a, say for example, a smooth system. When dealing with large quantities of gas, it is often more convenient to treat the gas as a continuous smooth substance with no gaps. Now you might have a question that why we are treating that there are no gaps. I will come to that part later. So here now you can see there is a question that why do we use the continuum model? Now compared to this one, which has got relatively vast spaces, if we get a gas or a kind of a system which has got this many amount of atoms and molecules, very dense, and the numbers are quite large. So the problems in dealing with large numbers, gases can be surprisingly dense, containing a large number of molecules in a small volume. So the continuum model is a useful tool for analyzing gases, but it only applies when the gas is dense enough and the system size is large compared to the mean free path of the molecule. So the problem in dealing with large numbers, continuum model helps out. Also what it helps is that if you consider the average properties the continuum model, it remains relatively constant. So when it remains relatively constant, what does it mean? It means that things will be much easier to calculate. So constant things are obviously easier to get, and that is why the next point, that continuum model allows us to use simpler mathematical equations. So if I take a very large number where the gases, the atoms, the molecules are quite in large, then we can use the continuum model, assuming these things to be smooth without any jumps. The average properties remain constant and the mathematical equations of these things becomes easier. So let us take an example. Imagine this is a glass of water, and if you took an infinitely small sip, what would it be water? The answer is obviously yes. And that is the idea behind the continuum idealization, right? Because we can talk about the density of water at any point, because even though it is made up of separate parts, the parts are so small and so close together that for most purposes we can act as if the water is completely smooth and continuous. So this continuum idealization is a powerful tool because it will allow you to use calculus and other mathematical techniques to analyze and predict the behavior of real world materials. It is a simplification, but it is a simplification that makes things a whole lot easier to deal with. So even though it is made of small parts, the parts are so small and close together that it would come as a water only. So here is a quick, I would say, a summary. This idealization, remember, it is valid as long as the size that we deal is relatively large. This is the case in practically all problem except some specialized cases. And the continuum idealization is implicit, and it makes a statement such as the density of water in a glass is the same at any point. So making the mathematical calculations, etc., easier. Now, in order to have a sense, now here we were talking that they are so large and so dense, etc. So in order to have a kind of a sense about the distances involved, let us take this example that consider a container, for example, this filled with oxygen at atmospheric conditions. Now the diameter of the oxygen, so consider a container filled with oxygen. Now the diameter of the oxygen molecule is about this much, 3 times 10 to the minus 10 m, and it is mass is 5.3 into 10 to the power minus 26 kg. Also by mean free path of oxygen at 1 atmosphere pressure at 20 degrees Celsius is 6.3 times 10 to the power minus 8 m. That means what? That means this particular oxygen molecule, it takes a time to travel a distance of 6.3 into 10 to the power minus an m, which is about 200 times its diameter till it collides with another molecule. So that means it travels about 200 times of its diameter before it collides with the blue molecule. So this is just an example in order to make you understand that how the distances, etc., are concerned in terms of mathematically simple equations. Now let us take this kind of a left hand side what you see. So there, say for example, there are about 3 times 10 to the power 6 molecules of oxygen in this tiny volume of 1.1 mm cube. So here at ATM 20 degrees Celsius, we have got 3 times 10 to the power 6 molecules of oxygen. So the continuum model is applicable as long as the characteristic length of the system, such as its diameter, is much larger than the mean free path of the molecules. So what am I trying to make out? So what is the basic idea that I'm trying to make this example? What I'm trying to say is this. Seemingly small volume of 1 mm cube can hold a vast number of molecules, this much, at a standard pressure and temperature, and this gives an idea to you that how dense gas can be at the microscopic level. Also, the concept of a continuum model is a very simplified way of treating material like a gas as if it were continuous and smooth, even though it is actually made up of discrete molecules. I would say discrete particles or molecules. Also, there are a few points. The continuum model is only and only applicable as long as the size of the system we are studying are much larger. At very high vacuums or very high elevations, for example 0.1 m for atmospheric air at an elevation of 100 km, it becomes large, and we need to use what is called a rarefied gas flow theory. And the mean free paths to the average distance molecules between collision with each other. Obviously, the mean free path means actually the average distance of the molecules. So continuum model are used where the molecules are closely packed and constantly colliding with each other. Rarefied gas model is used when the behavior of the gases, when they are very thin, meaning the molecules are far apart and collision between them are very infrequent. So depending upon the complexity of the system, depending upon the physics that we are doing, we can use either a continuum model or a rarefied gas. That depends on each other. Now from here we come to 3 very important concepts of I would say thermodynamics or physics. One which you already know, what is called density. Then we deal with specific volume, and then we start with specific gravity, coming up to the next part of the video. So we already know what is density. So it is a fundamental property of matter. It tells how much a mass is packed into a specific unit of volume. So rho equals to m by v, which is unit of kilogram per meter cube. Now it is just the reciprocal. That means just the opposite of reciprocal of density is the specific volume, which is small v equals to v by m. Now I would like to give you an example. Now let us imagine that you have a certain amount of material, that means water. So specific volume, what it does is that it tells you how much space that material occupies per units of its mass. Remember, specific volume is a measure of how much the material occupies per unit of mass. In simpler term, we can tell that how spread out is the material. That is what is called, we call that the specific volume. So the specific volume is, as you can see, V is calculated by dividing the volume capital V of a substance by its mass small m. And since it is a reciprocal of density, obviously the units will also reverse, isn't it, in the case of inverse of density. So in case of density we have got kilogram per meter cube. So for specific volume it will be meter cube per kilogram. Very simple. And we can also denote it by this, as you can, V equals to 12 m cube, m equals to 3 kilogram. So we can use the rho, that is the 0.25 kilogram per meter cube, and small v, that is the what we call the specific volume, would be this much. That's it. This is the concept. So specific volumes, so specific volumes and density are actually inversely proportional. What does that mean? Let us take the same kind of an example. We take this water of glass. So this means as the density of the substance, density means we are trying to make that more mass is packed in a given volume. As it goes up and up and up and up, so what will happen? The specific volume, which is less volume per unit mass, this will slowly go down. So the density of a substance increases, its specific volume decreases. And you can easily convert between density and specific volume using this relationship, which is simple. Specific volume equals 1 divided by density, and density equals 1 divided by specific volume. And yes, obviously one more thing which is very important is that in case we take a differential volume, because we would have to use calculus, which is del m, and we take a differential element of mass, which is del m, and a differential volume del v, then what would be happen? The density can be expressed as rho equals to del m by del v. That's it. That is how we mention what is called a specific volume, and we have already know what is the density. Now I would like to cite an example, and I will like to show you how it is. So for example, we already know that the density of a substance in general depends on temperature and pressure. So the density of most gases is proportional to pressure and inversely proportional to temperature. Now liquids and solids on the other hand are essentially incompressible substances, and the variation of their density essentially with a pressure is all negligible. Let's say for example, this is the water which is boiling at 20, I mean to say it is at 20 degrees Celsius. For example, the density of the water changes from 9998 kilogram per meter cube at 1 atmospheric pressure to 1003 kilogram per meter cube at 100 atm. What does that mean? That means there is a change of 0.5%. Similarly, the density of liquids and solids depends more strongly on the temperature than it does on pressure, obviously. And from here at 1 atm, for example, the density of water changes from 9998 kilogram per meter cube at 20 degrees Celsius to, say for example, 975 kilogram per meter cube. So it changes from 9998 per kilogram per meter cube at the same 20 degrees Celsius at 70, and it changes, then density changes to 975 kilogram per meter cube, and it does at 75 degrees Celsius. And how much it changes? It changes 2.3%. And this 2.3% is so negligible that we can neglect it in many kind of a physics and engineering analysis. So this is just a kind of a simple example which will make you understand that how the change in the density of the water from 20 degree at this changes to this one, and how it changes at the same 20 degree with mass of 998 degree at 1 atm and at 100 atm. Now from here we come to the concept of what is called the specific gravity, and this is why I have written sometimes the density of a substance is given relative to the density of a well-known substance, and we know that that relative term is nothing but water, H2O. So here is a quick example or a definition. You can say specific gravity is a relative measurement of density, and it obviously compares the substance with water. So we can say RD equals to rho of substance divided by rho reference. That means the substance divided by the reference. So the reciprocal density or reciprocal of density is the specific volume, which is defined as volume per unit mass, and specific gravity is what? Rho object divided by rho reference, which is now I have given as rho H2O because that is the standard of water. So specific gravity as a definition, it can be defined as this: the ratio of the density of a substance to the density of some substance, standard substance at a specified temperature. And remember, this is a very important point. Water we take at 4 degrees Celsius, where the rho H2O, that is the density, is 1000 kilogram per meter cube. And this is very important, that specific gravity of a substance is basically a dimensionless quantity. That means it really doesn't have any dimension. So the numerical value of the specific gravity is what? G per cm cube. So in the SI units, the numerical value of the specific gravity of a substance is equal to its density in G per cm cube. You can write it as kg per L also. And as you can see, yeah, kg per L, and since the density of water is 4 degrees Celsius, so it would be something like this. Now, if I take, say, for example, the density specific gravity of mercury at 0 degrees Celsius, for example, is 13.6. So, therefore, its density at 0 degrees centigrade is 13.6 gram per centimeter cube, which will be equal to this kg per liter, which will be equal to 13,600 kilogram per meter cube. And the specific gravities of some substances at 0 are given in this table, which you can look into now. These are some of the specific gravity table which is given, and it is very important to note that substances with specific gravities less than 1 are considered to be lighter than water, and hence they can float on water. So anything which floats on water, we can you can use this formula in order to calculate what is the specific gravity. It is it is something which is less than 1, then it would be sinking, and that it is 1, or then it would be specific gravity less than 1 would be lighter, and something which will sink inside. So here are a few of the things that if the density is equal to the density of reference material, then the specific gravity will be 1. Now from here we come to another important part, that if it is sinking and it is floating, what is called is a specific weight. So we got specific volume, we got specific gravity, we got density. Now we come to the next important concept, which is called specific weight. So specific weight, also it is known as unit weight and denoted by the Greek letter gamma, is a property that relates the weight of the material to its volume. And how do we denote that? Simple, gamma s equals to rho times g. And it essentially tells you how much more force acts per unit volume of a substance due to gravity. So here is the concept. Density tells you how much mass is packed into a volume, but specific weight goes a step further, and it tells, actually, since weight is the force exerted by gravity on the object, so specific weight tells how strong the gravitational force is per unit volume of the material. So ultimately again we come to the concept of gravity. So density will tell you how much mass a substance packs into the volume, and specific weight will be the force of gravity acting on its mass, and that is why you can see that the unit is Newton per meter cube. So obviously it would be something related to gravity. So from here we finally come to the final conclusion that density kilogram per meter cube, gravity because it is meter per second square, so specific weight would be Newton per meter cube. So the most important part is that it has got a gravitational dependence. So unlike density, which is fixed property, specific weight depends on gravity, and that is the reason gravity can vary slightly depending on the altitude and other factors, so specific weight will also change. And it can be comparison with density. I can tell that specific weight and density are related, but they are not the same. Density tells you how much mass is it in unit volume, while specific weight tells you the force exerted by gravity on that mass per unit volume. Let me give you a very simple numerical example. Imagine this as a cubic meter of water at sea level, where gravity is 9.81 meter per second square. The density of the water is 1000 kilogram per meter cube, and using the formula of specific weight of water, we can get gamma equals to this multiplied by this, which is approximately equals to 9810 Newton per meter cube. So that brings us to the end of today's lesson, where we learned a lot about density, specific volume, specific gravity, specific weight. We also learned about certain other things which are called the speed of the molecules, how they're hitting, the continuum model, the properties of a system, intensive and extensive properties. So I am really very thankful to you for those who have taken up time and watched my video. Thank you for watching this video. If you have liked it, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. And you can write to me at this email ID, and you can subscribe to my other channel, General Relativity Explained. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. And do let me know how is the series of thermodynamics going, because I have made it exclusively for you so that you can learn and keep on learning a lot. And watch Physics for Students, because I will be bringing you more and more important, fun-loving and surprising videos. Till then, goodbye.